The boiling points of linear hydrocarbons increase with increasing chain lengths, and for separating methane from heavier hydrocarbons such as ethane and propane, distillation trains are normally used in natural gas processing as pictured in this diagram. Adsorbents such as metal organic frameworks and zeolites offer alternatives to natural gas processing that relies on the differences in London van der Waals interactions of the guest components with the framework atoms of the adsorbent. The polarizability of the guest molecule increases with increasing chain lengths, and so does the London van der Waals interactions. It's quite interesting to note that despite what one would assume from the name London, Fritz Wolfgang London was actually German. And I'm partial to Johannes Diederik van der Waals, who got the Nobel Prize for Physics in 1910. He's, of course, well known for his van der Waals equation of state. And being a professor at the University of Amsterdam, I'm particularly proud of the early contributions of Jacobus van 't Hooft, who got the first Nobel Prize in Chemistry in 1901, and Johannes Diederik van der Waals, who obtained the Nobel Prize for Physics in 1910. So let us see how the London van der Waals interactions can be exploited to separate methane from heavier hydrocarbons in a scheme for natural gas processing that does not involve distillation separations that are energy intensive. Today I'm going to highlight the use of an ethynyl-modified interpenetrated MOF for natural gas purification. This MOF has been constructed by using expanded ethynyl-modified tetracarboxylate ligands and paddel-wheel building units of Cu2CO2-4. The work is described in this paper just published online in Dalton Transactions. To demonstrate the efficacy of the use of the ethynyl-modified interpenetrated MOF in natural gas purification, I present here transient breakthrough simulations for a feed mixture consisting of 6 components. This is an equimolar feed mixture of methane whose breakthrough is indicated by the green line. The red line indicates the breakthrough of carbon dioxide. The black line indicates the breakthrough of ethene or ethylene. The yellow line indicates the breakthrough of ethine or acetylene. The blue line indicates the breakthrough of ethane, and the pink line represents the breakthrough of propane. The y-axis is the dimensionless concentration at the exit of the fixed bed adsorber packed with the MOF particles. The x-axis is a modified time axis where Q0 is the flow rate of the gas mixture at the inlet in units of liters per second. T is the time in seconds. M sub ads is the mass of adsorbent in the bed. The units of the x-axis is liters per kilogram. We note that purified methane can be recovered during the early stages of the transients, and the sequence of breakthroughs follows the sequence of adsorption strengths that are largely dictated by the polarizability of the molecules. We have methane followed by carbon dioxide, followed by ethene, followed by ethine, followed by ethane, and the last component to breakthrough is propane. The transient breakthrough simulation methodology is described on my YouTube channel.